Disruptors and curious minds, welcome to another episode of Thinking on Paper. This is your personal guide to understand how emerging technologies are affecting business, society, and the human condition in general. My name is Jeremy. This is Mark with me. Mark, what are we talking about today? What are we getting into?
Today is a story of getting quantum computing out of the lab and solving humanity's biggest challenges. So it's a small subject, a small show today.
Just a wee
Um,
bit.
yeah, if you're working or learning about quantum, if you've been following thinking on paper for a while, you'll obviously know about quantum's potential. We had Google announcing last year that Willow solved a calculation that would take a supercomputer 1 billion years. We had IBM on here not long ago talking about 600,000, dare I call them, hobbyist developers in their sandbox. But where we need to get the quantum out of the lab and into the real world, we need to harness nature, don't we? We need to, I don't know, replace the Haber-Bosch process. We need to energize the world. We need to put the damn fires out, don't we? So
My gosh,
yeah,
no doubt.
and today's guest is going to explain about a competition that's, I believe, sponsored a bit by Google, that's going to incentivize scientists, entrepreneurs, and builders to do exactly that.
Guys, keep in mind too, it's a brand new year. We've got new segments. We've got our hot button questions. We've got our thinking on paper news. We have our debrief at the end. Hope you guys are enjoying that thus far. But we're excited to keep this thing moving and keeping it valuable for you. So let us know how we're doing too.
And on the hot buttons, there's a really good hot button question today, so you want to stay tuned for that because I think you'll want to answer it as well, Jeremy.
I'm in. I'm in. So who are we talking to today?
We're talking to Kathrin Spendier, who is the technical prize director of XPRIZE. Welcome to the show, Kathrin. Thank you for being here.
Hi, Jeremy. Hi, Mark. Thanks for having me. It's going to be a lot of fun, I think. The hot button. Yes.
Oh,
It's all about the hot buttons.
excellent. Yeah, I think we were talking a little bit in the pre-production chat. I originally learned about XPRIZE when I read a book by Peter Diamandis called Bold that was talking about just these really big ideas, how to push the boundaries of what you think you're capable of, what society thinks they're capable of. And part of that led into this whole idea of XPRIZE and incentivizing and creating challenges, getting really smart, curious, interdisciplinary people together to stir the pot, and I think it's amazing. So we want to get into this this and a little bit about quantum computing as well, but I want to start off with one question related to what do you tell your friends, your family, at dinner when you pull them aside and you want to give them like a little bit of insight, a little bit of a head start into what quantum computing could mean for our society? What do you tell them?
So typically, when we have that dinner conversation about quantum computing, I do have it sometimes with my kids, and I try to understand it. And I tell them that, calculations take time. And when we solve really tough problems, it takes us a long time for the computer to solve problems, sometimes days and weeks. And quantum computing will be able to solve some problems faster. So we don't have to wait for days and weeks, so we can have answers right away. Imagine you go to doctor, you will have a disease, and they try to figure out how to help you with the right, medicine, for example. They could do like analysis on your symptoms very, very fast, by looking at a lot of data, right? So it's kind of like this kind of like aha moment that we don't have to wait to get answers for a long time. But I tell them it's not going to be, for everything we're going to apply it. It's going to be very specific problems because the quantum language is complicated, and you have to like talk in the language the quantum computer understands. So that's pretty much it. So we want to really speed up the tough problems where right now we either take a really long time or we can't even solve it exactly because the classical language actually does not really understand that problem well. So we actually want to use quantum language to solve that problem.
Could you give us a couple of examples of what those kind of problems might be that a classical computer just simply can't handle?
Yeah, one is, as I think people in the field know a lot about, it's kind of like material science, quantum chemistry calculations. Everything is based on a Schrödinger equation that is purely quantum mechanics. And because of that, the electronic states and the way, you have different energy levels, that language is encoded in the quantum mechanics. So it turns out that the classical compute right now, we have to do estimates, we have to do like DFT or other like approximations. We can't solve it exactly at the moment. So we live with approximations, and sometimes we say, okay, it's like 80% okay or 70% okay. It's good enough for us to, for example, start a clinical trial on a drug or like develop materials. But in principle, you want to solve it exactly, because you do want to like make that leap of solving bigger problems. That's one example, for example.
One follow-on question on that, and I'm not a math guy. I'm math adjacent, math curious maybe. Is it true that calculus is actually a lot of approximation, just approximated very specifically?
Oh, it depends on what you do. So when we apply, I have a physics background, I have a physics PhD. And when we solve certain problems, we use calculus, differential equations, partial differential equations. And we are building the equations out. We are trying to put in the different terms, like force terms, friction terms, whatever it is, energy terms, like we have to estimate a potential energy, for example, has a certain shape. And then we put that in, we estimate that, and then we try to calculate it. And typically we can't do a lot of stuff analytical. Then we have to go numerical. And once you are doing numerical analysis, everything is just encoding, right? So how do you encode like an integral, right? You have to slice it up in small pieces. It's never exact. It's discrete. So in any case, this is kind of like, yeah, I agree with you. If you apply calculus, you have to kind of make these approximations and kind of put it in your math.
Anyone who's wondering about coding in integral, I didn't get it either, so don't worry.
So great. Thanks for that answer. So if you're listening and you want to get into rabbit holes about quantum mechanics, and that we have tons of episodes that Mark will post in these show notes that dive into what quantum mechanics is, because we live and we think in a Newtonian world where quantum mechanics is very opposite that. And that's why it's hard to get our head around things like quantum computing. So dive into those links if you want to dive in further. But I want to understand more about XPRIZE and your role at XPRIZE. And let's start with, what is XPRIZE, and what are you trying to solve with the framework?
Yes, so XPRIZE it's an amazing nonprofit foundation, and it's around 30 years, and it's kind of started with the Ansari XPRIZE, where we try to get the community, like make space travel, open for anyone, so make it available for private sector. 30 years ago, space travel was only government sector, right? And we really wanted to bring the space travel to the public, right? And then Ansari Prize was launched, and it took 10 years to get funded. But in any case, we solved the tough problem of, the teams did, of traveling to space for like once with a rocket, right, and come back and do it again within 2 weeks, I believe. It was a $10 million prize purse, but like teams spent millions of dollars, $100 million on the solution. The solution then turned into Virgin Galactic and so on. So pretty much, I think that kind of explains what XPRIZE is. It's trying to find something where we as humanity kind of got stuck, or something didn't change for a long time, and we're kind of like going with a very old technology, or we haven't really like solved the big problem. And then we're trying to, with XPRIZE, we try to have an audacious goal. We really push ourselves to like solve something really, really tough, so that our life on Earth is better, right? So it's an impact for all of us, a positive impact for all of us. And then we kind of incentivize that with a very nice cash prize. And
That always
then,
helps, right?
yeah, it helps, right? So pretty much we're trying to crowdsource a solution to a really tough problem that helps humanity to make big leaps that we need to make in order to have, a fulfilled living, in order for us to have, everything we need, an abundant life, for all of us, where we feel like we want to better the world, right? That's why we're here. And XPRIZE is trying to solve these tough problems to better the world.
Did you say that so Virgin Galactic came from the original XPRIZE?
Yeah, the IP from the original XPRIZE.
Awesome. Jeremy, I've got a question for you. This isn't new in terms of competition pushing humanity to better things. I believe, like Phileas Fogg, that was a competition. The old geography institutes in London, a lot of the early clubs of London were built on competition, on challenging explorers, on challenging scientists to break new ground. It's not new. It's been replicated now. What is it about competition, for you, Jeremy? What is it about the competition that drives these advancements more quickly than non-competition? Do you think?
I-
Before we pass that over.
No,
Yeah, Kathrin, what do you think? Fire away. Yeah.
No, for me, like I was a downhill ski racer for many, many years. I tried to become an Olympic downhill ski racer, and competition just is where to get the best out of yourself. If you are in a field, you were really connected to the prize and it resonates for you, and you really like want to solve the problem, and you are competing against others, it just takes you into a certain mindset. And all of these competitions are more than just you solving a problem. It's about making an ecosystem. You have to develop a team that has different expertise, right? For example, like we also have a wildfire XPRIZE right now, right? So where we have our wildfire specialists have to talk to people who have the technology, who can actually, for example, detect wildfires faster and put them out. So you have to talk to engineers, right? You have to talk to people who understand weather patterns. Like you have to bring in different people from domain expertise, the engineers, and then you have to maybe put it together, like even like an entrepreneur, right? Who knows how to like implement something quickly. So this is about XPRIZE. XPRIZE brings these people together because we have a global competition, and we have done it for so many years. We have a very good, I think we're 30,000 individuals that joined the competitions over the 30 years. So we have a huge network. And then once the solutions are developed through these milestones, we also bring in investors that can help the teams develop the technologies, right? And as we do that too, we're also trying not just to say, oh, they have achieved a goal. We're also trying to come up with the metrics that define that kind of what defines to like reach this XPRIZE, right? So what metrics do you have to like check the checkbox, right? And that's actually, we have to talk with experts in the field. That's not easy. And benchmarking a field is typically very difficult. Sometimes we have a lot of different benchmarks and no one agrees. And we hope through a prize, we can actually pull everyone together and they all agree, yes, that's a good benchmark, that's a good metric. And then we try to push that moving forward.
I love that answer, and I think the one thing that I would add to that, I mean, I think all of us innately have a little bit of competitive vibe. Although my wife would argue that she doesn't have a competitive bone in her body, but I think there's a little bit in there somewhere in all of us. But tell me about what you think the power of constraints does within the prize environment, because I'm assuming there's a certain, hey, this contest starts today and we go for this amount of time, because a lot of big thinkers can like stay up in the air, and you got to land the plane at some point, right? So tell me
Right.
about the power of constraints in this.
Yes, thanks for bringing that up. It's definitely like, so depending on how audacious a prize is and how important it is to like reach a milestone as humanity, we define the prize timeline, right? So some prizes are for 3 years, some are for 5, some are for 7, right? Depends on how audacious the prize and what milestones you have to do. For our health span prize, you have to do actual like clinical trials. So that takes time to do, right? We want to accelerate it, but we still have to have time for that. So that's why the price is a little bit longer. Wildfire, XPRIZE Wildfire is 4 years, right? If the price would have started, 4 years ago, maybe we could have helped, now the fires in Los Angeles, right? But this is very urgent. We have to like get to the solution as soon as possible. So there are experts. We are consulting in the field that we have identified that kind of got stuck. It needs something that comes out in order to accelerate whatever technology we have, and then we define a timeline. It also depends on the price purse, it depends on how much testing there is, and so on. So it's a little bit of a mix of like what's possible, what's needed, and how urgent things are.
How long is the Quantum XPRIZE competition running for?
So the Quantum XPRIZE started March of 24. It's almost running now, a year, and it's until 27, early 27. So it's pretty much a 3-year prize.
Okay. You mentioned constraints, and there's also constraints on what you're actually looking for in this competition. So novel algorithms, new applications, enhanced performance. So could you speak through each one of those constraints and how they apply to the prize?
Yeah, so maybe I can like give a little bit more, background, so we can lead into this. So the XPRIZE Quantum Applications Prize, where I'm the technical prize director for, and it's pretty much a 3-year competition sponsored sponsored by Google Quantum AI and Jester, Geneva Science and Diplomacy Anticipator out of Geneva. And pretty much it was designed based on the fact that at the moment we don't have hardware that, can do very powerful calculations. It's still kind of sandbox stage, but we are like making big leaps. But in 2030, we are thinking that we're going to have hardware that's starting to get exciting. So, but unfortunately, even though if you would have the hardware right now, we don't have many algorithms that can actually solve minimum problems. We have a certain like 2 handfuls of algorithms, Shor algorithm, Grover's algorithm, that have shown a quantum speed up, right? Quantum advantage, theoretical, but really their application is limited, right? So really what we need more algorithms that solve meaningful problems that all of us care about and actually improves our life, right? Has social impact. And pretty much now with XPRIZE Quantum application, we are crowdsourcing that algorithm. The reason why we have multiple ways of competitors to join the competition, as you said, we have developed a novel new algorithm for a application of societal good. Take an algorithm we already have, but show that you actually can apply it to a meaningful problem for society, or take an algorithm we already know that has the application, but try to reduce the resources needed, right? So come up with a better algorithm so the calculation is more near term. And since we don't know what's out there, because we have like 1 or 2 algorithms every decade, so we haven't been very good at doing algorithm development in quantum computing.
Why do you think that is?
So
Can I play my silly question card before you
Yeah.
answer that as well? And can we look? We had Horizon on a few months ago, and he was speaking about algorithm. Is it okay for our listeners to think of quantum algorithms as software upon the hardware? You mentioned hardware. When you mention, should we be thinking of algorithms completely differently to software in a traditional sense, or is that an okay analogy to use?
So pretty much the way I think about algorithms is if you can imagine like a stack, right? On the bottom you have your hardware, on the top you have your application, right? So you have to take the application and you have to encode it into the language of the quantum computer, like at the first level, right? Just into using quantum mechanics, right? Using kind of like gate-based quantum computing or annealing or whatever you do. And that encoding from the problem to that whatever hardware you're using, like kind of like first layer, that is the algorithm. And then you still have to, once you have the algorithm, right, you still have to, for example, the algorithm tells you you have to run a certain number of gates, a certain number of qubits. Then you still have all the software layer that has to compile the algorithm into the language the quantum computer understands. And then you have the control layer where you have to tell the quantum computer, if you have trapped ions, for example, you have to tell them how to like move around on the chip, if you can control them, right? And then you have to read it all out. So it's kind of like different layers, and you have software, hardware, controls, you have compilation, everything plays in it. But for me, the algorithm is really, you take the problem and you like do the first kind of like algorithm, how you encode it is the kind of the starting point of the stack.
That's a great question and a great explanation on that. So going back to the fact that we haven't had a lot of algorithms come out over the last 10 years or so, what do you think the main reason for that is?
So in my opinion, man, if you start studying quantum information science, you learn, linear algebra, and then you go into like kind of like probability, and you go into like trying to like encode your problem into waves. That's pretty much what you're doing. You work with the Hamiltonian, right? And if you think about the way it goes, if you work with the Hamiltonian, if you go down to the basics of it, and the way you define it, you are adding different waves of different amplitude and different phases. And just imagine you have to encode your problem into that kind of language. And then the right solution should have an interference of your waves that are constructively interfering, high amplitude. And the solutions you don't care about will destructively interfere and have a low amplitude. And that's just very complicated, right? To think about that. So having the math, understanding how you can massage that Hamiltonian with the right terms to do what you want it to be doing is very difficult, and you have to really understand it. And the algorithm is not just a classic, like a quantum algorithm from the start to the finish. It actually kind of has a lot of classical compute in it. And then there are some parts of the algorithm, some primitives in the algorithm you're going to take out, and then you want to speed them up with a quantum way of solving something, and then you go back. So a quantum algorithm is not just pure quantum, it actually has a classical workflow, and then you have your quantumness in it, for example, and then you keep going. And that's difficult.
Kathrin, I'm going to create some t-shirts, and I'll be sure to give you a part of the revenue. The t-shirt's going to say massaging the Hamiltonian. And we're going to use that as a vehicle to promote the power of quantum computing. I think that's awesome. So
how important is it to know what a Hamiltonian is?
If you want to develop a quantum algorithm for XPRIZE quantum applications, it's very important that you know what a Hamiltonian is. So.
Just for our listeners in one sentence.
Pardon me?
For our listeners in one sentence, Kathrin, a Hamiltonian.
It's pretty much it's an energy. Like you're trying to like describe energy landscape.
Okay. Let me try and use an analogy here, and you know, shut me down if I'm going the wrong way on this, Kathrin. But like you mentioned, the idea of quantum algorithms needing to look at multiple wavelengths, multiple paths of a potential thing happening, right? When we're in traditional math, we just look at, okay, this thing's going to happen if I do this thing. Instead of that, we look at, it's more, are we in the like path integral area of like, I have to look at all the possible paths and consider a calculation upon all of those possible paths instead of just between A and B? Is that close?
Yeah, so I have to be honest with you. I'm not a quantum information scientist, expert. So it is very like subtle how you do that, and you really have to understand how kind of like the mathematics works out with this interference. And then you have entanglement, which is on top of understanding interference and of waves, and then you have obviously different energy levels, the way you encode your problem. So it's fairly complicated. So it depends on the problem you're applying and so on. So just you have to be an expert.
Makes total sense. Mark, I'm sorry, I've already rabbit holed.
Does
I've
it
got
depend on the type of quantum computer as well that you're using.
So for XPRIZE quantum applications, you can do any quantum computer, any modality. Pretty much very wide application space, as I explained to you before, because we really need to like improve the number of algorithms we have. So out of all of these algorithms, we got some pretty cool tools, quantum tools, like a quantum Fourier transform, for example, a quantum phase estimation. They came out of these like algorithms, and we're trying to reuse them for different problems, but we really haven't like improved our toolkit. Ideally, you want hundreds of algorithms, right? And we're just not there.
Okay. I've got one more rabbit hole question, Mark, and I'll be done, and we can move on. But
rabbit holes are good. Keep going.
So we've talked about this in our quantum season kind of thread a little bit, but nature does quantum really, really well. Like nature's awesome at quantum mechanical processes, right? We talk about photosynthesis, right? For instance, is has that piece in it. Is anyone out there like, and this is so silly, but is anyone out there like looking at photosynthesis and how to maybe repeat how it does it and apply what you learn to quantum computing? Is that even a thing, or?
Oh, quantum is now going more into biology. That's for sure. I actually taught a course when I was back at a university before. I joined the industry, and now I'm a nonprofit. I taught a course on photosynthesis, like in my biophysics course, and it's we actually don't fully understand how photosynthesis works. There's some tunneling part to it. It's fairly complicated regarding like the different players during photosynthesis. People say that possibly quantum computing could help with that, but there's no algorithm at the moment. I am aware that describes that process.
Well, it's kind of one of those things like photosynthesis or quantum computing could help figure out photosynthesis, but photosynthesis could also figure out how to be a better quantum computer in a way, kind of, right?
But there's this idea of using nature, right? Going down to the atomic level and use atoms to do the computation. But that's what trapped ions is, for example. So trapped ions quantum computers, you're using an ion, right, for computation. And that's like, that's nature you're using for computation because you're starting with something very pure, right? And it uses quantum mechanics, right, in order to have changed the properties over time. So it's a very natural like modality for quantum computing. And I think people are exploring these different modalities. Photons, for example, is another one where we actually want to use nature to do the computation in the quantum computer. So yes, the space is wide, and we need more people to ask these questions. What else can we use for compute?
Hence the XPRIZE.
Hence the XPRIZE, yes.
Awesome. What, and I know you may not be able to share too many details on this, and that's fine, but what are the most interesting things bubbling up from these prize groups, or not necessarily the prize groups, but maybe some of the activity that's come out of this research? What are some of the things that are bubbling up that are getting you like really excited related to quantum computing and applying it to something, as people say, applicable to making the world a better place?
Yeah, so what for XPRIZE quantum applications right now, we just started the competition, so we haven't, you know, the teams have not submitted their solutions yet. They will have an interim report, which is kind of like the first status check-in. But like phase one submissions will be in August of this year, and then by the end of the year, December, we're going to have up to 20 finalists. That will share the $1 million prize purse, because the prize is $5 million overall. So the first milestone will be $1 million. So 20 teams, up to 20 teams will share that. We'll know that in December. And then we hope that, we're gonna be able to answer the questions. At the moment, what teams have shared with us is kind of like, 20% of the teams want to like solve some sustainability problems, for example, or the UN SDGs, which are, really like tough problems, and there's a roadmap for that. So yeah, so it's a typical, at the moment, what we know from our cohort, it's a typical application space, material science, drug development, optimization, for example, that you can apply for different applications. One of them kind of is, what kind of like what you would expect, but again, we only have had a little bit of a small, view of it, and we will know more by the end of this year.
Amazing. And you said 24 teams?
So up to 20 teams will be finalists and move on to phase two, which starts in January 2026. But right now, we have 300 teams from 46 countries that are in the competition. And it's like anyone from a student or like individual that starts quantum computing, so some individuals that are in it for decades. We have like, startups, we have universities, we have established startups, we have universities, we have people that just starting their journey to build a company, right? They want to use XPRIZE to do that. So we have like physicists, engineers, chemists, biologists, people from healthcare, from finance. They all come together, right, and form very multidisciplinary teams and interdisciplinary teams. So it's just very exciting. And then we have 46 countries, so we do have like kind of like all the regions in the world. The US is mostly like represented in Canada and then Europe, but we also have like, like Africa is, for example, in it, right? So we also have, Australia in it, New Zealand, we have some like Asian representation. So we also have South America in the mix. It's very exciting.
Dare we call this the Quantum Olympics, Mark?
That'd be something, yes, yeah.
That would be something. Well, I think we're going to get into the hot buttons in a minute, but I just want to ask a question. I don't mean to be disingenuous about this, but I think I should ask it. There was, reading through the comments on YouTube, there's quite a lot of people asking the question that essentially when 40 billion is being invested in quantum every year, 5 million divided by 5 winners, and it doesn't seem that much. Is that by design? Is that because by that way you maybe get the smaller students involved, you get people who wouldn't normally be involved? Is this a constraint in you'd like to offer more money for the prize? Like, could you speak through that to that?
Yeah, of course, of course I can. So it's a 5 million prize purse. So then after the 1 million, up to 3 winners will share $3 million, and then some runner ups at the end will share 2 to 5 will share 1 million when we announce the finalists in 2027. But the prize purse is kind of like, we had like a IBM Watson, which is similar timeline with a similar price purse. This prize is purely theoretical. So I want to say that it's a thinking on paper prize.
Hey.
Yes, yes, thinking on paper prize, because it's purely about developing an algorithm on paper and mathematically prove that you have quantum advantage by, then also comparing to the best classical algorithm. So that being said, there's no testing involved, and there's other things that normally typically XPRIZE has, where teams have to like develop like some technology, and you have to test stick facilities and such. It all costs money, but this is purely like an algorithm development price, and it's in the right size for other algorithm development prices. And it's a good incentive, and it's money that we give you without any strings attached. So you obviously have to pay taxes on it, but then you can do whatever you want with that money, which is great. And then really for people that are starting in a quantum ecosystem, like $1 million or $3 million without strings attached is a lot of money for young startups. It's actually like the right amount of money for software or like algorithm development startups. Not the right money for hardware, but it's not a hardware price. It's an algorithm price.
The no strings attached piece is the most powerful, and I love the thinking on paper prize. That's
Yes.
incredible. We're happy to partner with you guys on that if you'd like to include that. But
Seriously, though, I think that's a good clarification, because like if you're not deep into this and you read the website and you read about XPRIZE, you might think, okay, I want a finished product that's solving some incredible challenge to humanity, and I want it here on a plate, and there's your money. So it's not actually asking for that. It's the theoretical algorithmic proof rather than something more.
Right. Yes.
it's the recipe, not the steak dinner.
There you go.
Right.
Couldn't have put it better myself.
All right, are you ready? Are you ready for hot buttons? Do you want to stretch? You want to stretch out a little
Yes.
bit?
I'll
And
stretch out a little bit.
what? All right, Mark, are you ready?
I'm ready. Let's go. Hot buttons. Show me the clock.
And we're on.
What's the best book on quantum our listeners should read?
By Seilinger, Dancing with the Photons, by Austrian hero, Nobel
Okay.
laureate, and
Are we
Nobel
living?
Academia.
Are we living in a simulation? Yes or no?
No,
Einstein or Bohr?
Einstein.
AI, quantum's master or quantum's assistant?
Assistant.
What's the most pressing challenge for humanity that quantum will solve? First.
Clean water.
Oh yes, that's 5
Ooh,
out of 5.
we almost did it. That was great.
I think we did that.
Great job, Kathrin. That was awesome.
Could you repeat the book again, please? Sorry.
By Anton Seilinger, Dancing with the Photons.
Dancing with the Photons. Okay, I like the title.
Have you read Dancing with the Wooly Master?
No, but now I need to.
That was the first quantum book that I can't remember. We'll have to post this in the notes. But that was the first quantum mechanical book that I read, and I was like, whoa, and that like jumped me in. Well, surely you must be joking. Mr. Feynman was another one, but yeah, we'll post all of these. Thanks for participating in the hot button.
Dance of the Photons. Like, I get that right now.
Dance of the Photons.
And to you, Jeremy, are we living in a simulation? Yes or no?
That is such a hard one.
Yes or no?
No. Because I believe in us. All right, guess what time it is? It's time for the news. All right, we're in thinking on paper news. A couple things that's still happening. We're still in the wake of CES that has happened, where a lot of new technology kind of gets pushed out there and that sort of thing. The CEO of NVIDIA is obviously very very outwardly spoken about theories and all of that stuff, stating that quantum is he's betting about 20 years away. What are your thoughts on his view of the timeline for what they call quantum utility?
So it's really like hard to say, right? But if you really say like a quantum advantage problem with real world impact, clean water, for example. I do believe we're going to need decades for getting there to have that kind of computational power. But for more near-term applications where you can have an algorithm that is lose less resources, it could happen in 2, 3, no, not like 5-ish years or less. It really depends on the hardware, on our hardware providers, how quickly they can do things. Yeah, it might be
I think
niche applications first, probably very niche applications that are fitting quantum compute very well.
I think so. And I think also like when people think about what a new industry is, just the general public, and general public, if I'm off the mark, hit me in the comments and let me know. But a lot of times when new industries come out, the general public tend to evaluate how that new industry is doing, but by what Wall Street is saying and by what investment is saying and that sort of thing. And this is not a blink and we're here kind of thing. This is changing the way that computers think, changing the way that we ask questions for computers to solve, right? So it's a bigger play, and maybe, dare I say, we require a little more patience. What do you think?
Yes, I think the patients we know exactly what the pathway is. We know what kind of hardware we need, and it's about the scaling because we need going to need thousands of almost perfect qubits, like very good qubits, and we still right now trying to build one, logical qubit that is at that range of error. So once we have one of them, we have to have thousands or millions of these qubits to solve the problems. That's why it takes some time to build the hardware. But during that roadmap or that path, there's going to be problems we can do on the way that are going to be very interesting.
Celebrate the
We're so
wins.
notoriously bad at predicting things we know about, and overestimate what we can do in the short term, underestimate what we can do in the long term. I'm sure that I've read some paper that 20 years is just this number that people pick out of the ether when they want to be seen to be predicting a long way in the future, rather than saying 5 years, because there's like this human inbuilt mechanism to kind of keep it in your lifetime, to keep it relevant to you. And as soon as you start projecting out beyond your lifetime, so in 30 years, he'll be dead. So it's no point in him saying, in 30 years, because he's got this inbuilt mechanism to make it relevant to himself.
Yeah. Once you have like 100 logical qubits, you might be able to do something really cool already. So, and that could be, with less than 5 years. Like could be in 3
What
years.
isn't Willow? Didn't they say Willow was 100 and something? Or is that a different kind of?
So these are called physical qubits. So these are the pure state qubits. So you have to have an ensemble of these physical qubits that you make work together to make a logical qubit with less error than the physical qubit itself has. That's what it is. And we need to build that.
So this goes into our next question, our number 2 news item. This week, we talked about error correction a little bit. I think a lot of our listeners have heard about this Willow announcement that Google put out there. Can you help us, even from a high level, kind of unpack what that announcement? I knew it was largely around some error correction stuff. I mean,
Yes.
speed of calculation, but can you break that down? What the importance of the Willow announcement was from Google?
Yeah, for me personally, the announcement was really on error correction, as you mentioned. It showed that as you are having more physical qubits work together, as you increase the number of physical qubits, you decrease the error of the logical qubits. And it's predictable and it's scalable if you can just build bigger and bigger devices. And that's a milestone. That's amazing to show show an actual hardware that this scales. So now you can extrapolate, and now you know how many physical qubits you would need in order to make a logical qubit, right? Of a certain error rate. So obviously they need to still improve their hardware, but they have now shown that it's scalable, and that as they increase the number of physical qubits, their logical qubit error doesn't get worse. And that's the crux of it. So it's better. That was the main announcement in my opinion out of that paper.
Mark, you and I have talked about this on previous shows. And Kathrin, I'd love your thoughts on this. The idea of like more qubits so you have redundancy, or building a better qubit to not need the redundancy. I've been hearing kind of 2 schools of thought. Is there any truth to that? And what do you think, in your opinion, what's the best approach, at least from the information that you have today?
I believe that we still need to have better qubits. So the fidelity of qubits has to improve. So right now we make one error out of like 1,000. We should get to like one error of 10 thousandths, and then when that happens, then we can think about the ensemble. That's my opinion, but it's more like an engineering problem, right? So how many qubits can you put in a fridge? How big can you make a delusional fridge, right? When there are size constraints to it, and then maybe not science, maybe just power constraints, because you have to cool a really big delusional fridge. So we are trying now to like use delusional fridges to connect them, or we're trying to bring the GPUs inside the fridge. So we're trying to figure out how we can, like make this engineering problem overcome, and that depends on the modality and depends on how the scaling works.
So if Mark wants to become a better snowboarder, he can probably go in the gym, do some squats, maybe work on, his balance, that sort of thing. How do you build a better qubit?
I have to ask the hardware specialists on that. I don't know.
Just to call out for our episode with D-Wave to build more on what Jemmy was asking about the fidelity of the qubits, because I think that D-Wave use an alternative method where they want quantity over quality. So check that episode; it'll be just here if you're watching on YouTube.
Outstanding. Kathrin, this has been a super fun discussion. I know we have, it's time for the carryover question. Mark, this is another one of our fun segments. We like to thread these shows together. Mark, can you remind Kathrin what the carryover question was from our last guest?
I sure can. Do I have some music? I don't have any music. Hold on.
Oh, I don't have a cue for the carryover yet. I'm going to work on that. That's my homework.
Okay. So the carryover question is continuing the Willow conversation, because our last guest, they were working in AI, but they were interested in quantum. And I don't have the exact words, but essentially Willow solved a computation that would take a supercomputer 1 billion years or something to solve. And one of the theories he heard about how it did that was quantum tunneling, like between worlds, the multiverse theory. Do you think that is how it achieved it? And if not, what could be another explanation for it?
So I am based on just understanding the test. So it's called, random circuit sampling test. It's a very specific benchmark that has been used by Google and others. And pretty much what you do is you are taking a certain number of qubits and you're applying gates, a random set of gates to them over and over and over again. So you're mixing up their state, like you randomize stuff, right? And
Real quick clarification. Sorry to cut you off. Gates. Talk to me about a gate. Is that a thing that open and closes literally, or?
Yep. You can think about it classically. Like in classical, you have like your voltage going high, low, right? And the gates have certain way of like letting that voltage pass or not, and that's how you like make your algorithm. Quantum computing, it's similar. Like in quantum computing, a gate is like you kind of like have a qubit that is represented in like we call it like a kind of like a sphere. And more or less like it's a vector, and then it's like on a sphere, and the gates kind of like move that vector around, rotate the vector, and that's how you encode it. So that in essence you have like a qubit, you by these gates and you do it randomly, but then you can also entangle two qubits so that if you move this, that vector might move like that. So there's like a certain instructions, and then you kind of like add these instructions and randomly with a random way of like selecting these 2 qubit gates and single qubit gates, and then you read out the result. And it turns out mathematically, what the way I understand is like that you do the computation. So like when you have a qubit, you have 2 to the n kind of like states you can explore. If you have 60 qubits, you have then like 2 to the 60, right? Now, if you do a gate, you actually have a tensor product. Now you have 2 to the 60 times 2 to the 60. So now you have like 200 to the 130 possibilities you have to encode just for one step in your calculation. And that's why classically, if you think about the matrix with having 10 to the 30 entries and you try to encode that just takes a really long time.
That makes sense. So gates within qubits, adding gates to qubits creates more potential for those qubits to do something. Is that accurate or no?
It's kind of like changing their like it's the state vector. Like it kind of like you're like you're given different instructions. So it's, I don't know exactly to explain that, but it's just kind of, you develop like a probability distribution, and then you sample that, and every time you sample it, you get some more data right out of, and then you get some random, kind of like random like output of some of the states being high and some of them being low, and it's just really hard for the classical compute to do that. I want to say, like, some of these algorithms that we develop, when you look at these matrices, some of them are sparse, have certain characteristics, and that's why we can actually still solve some algorithms, even though we think we have quantum advantage even fast with a classical compute, because there are some structures in these matrices that classical can actually solve very well. But when you do this random slash on like 60 qubits with like 40 layers of gates, and it's just getting too much for classical to keep up.
Got it. But it's teamwork still with classical at the moment.
Yes, but I'm just saying this specific test shows the powerfulness of a quantum computer. It has no real application. Random sampling is purely a benchmark, but it's just very powerful the way it does it, that the classical can't keep up.
And so we read Quantum Supremacy, Michio Kaku, in book club, and he spoke about tunneling. And just to go back, I don't, you might have answered beyond my pay grade for that one. But so this idea of tunneling between quantum realms or worlds is a non-starter for you. That's not what's happening.
I think for me personally, I am more mathematical. I like what I see on paper. I'm thinking on paper, and and I think if you are in multiverse, if you understand the multiverse a little bit more and you believe in it, and kind of like on that kind of idea, and it's something that resonates with you, I think people have taken that approach. And there are people that talk about this, as you pointed out. But for me personally, I feel very good at having the math in front of me.
Excellent.
That makes sense. Yeah, I think where our heads were going during the last discussion in the last episode was like, okay, we're going to spin up this wormhole and throw a calculation in here. We're going to spin up this wormhole and throw a calculation in there, and that's how it's just it's just how it kind of spins up in your head. But math, think on paper, 100%. I love it. What about a carryover question for our next guest, Kathrin?
Yeah, so thanks for invitation to have me like post one. And for me, it's really about like, say that we have quantum computing or AI or like artificial intelligence, and having that self-thinking AI coming on. Like, so how do we make sure that everyone can use that technology, right? And it has a good, it's there for social good, right? That we make sure it's applied for social goodness and not for the applications we don't want it applied to. So how do we, as a society, how you ensure that?
Deep, good, nice question.
It's a great question. It's, technology has the power for good and bad within it, and it falls back on humans, at least at the moment, to make sure we do the right thing. But I love the idea of having a mechanism to grade for that, and that's fantastic. This conversation's been
ever been only used for good. Is there an example of a technology that hasn't been used for nefarious uses as well as noble?
Man, it's just think about quantum computing, right? I'm just saying, like everyone is worried about quantum computing, like cracking RSA, right? That seems to take the headline over other things, right? Anyways, like, we can protect for these things. But I'm just saying, I think there's technology we have used different ways. I don't want to point anything out now. I'm sure I can think of something, but it might take a little longer.
So the human is still an important cog in the wheel, no matter the technology, and thinking on paper is still a recommended approach. I love it. Kathrin, this has been a fantastic discussion. I would love to stay in touch with you as you figure out what this brilliant group of applicants and eventually prize winners are going to do to this. We'd love an update at some point.
The prize winners on the show.
It'd be amazing. It'd be amazing.
It was so much fun. Yeah, thank you.
Thanks for
the best show I joined thus far in XPRIZE, that's for sure. And if for everyone, please check out xprize.org. We have other prizes and some cool stuff that is boiling. So
absolutely, we'll be sure to share a bunch of links in the show notes and that sort of thing. And thanks again for joining. Have a great rest of your day. Thank you so much, Kathrin.
Thank you. You too.
Thank you.
Bye.
Bye.
All right. Disruptors and curious minds, we are now backstage after a fantastic conversation with the quantum technical director for XPRIZE. I leave
Prize director.
prize director. I leave conversations like this, Mark, absolutely inspired and renewed in kind of humanity's ability to do the right thing if situations are designed properly. I think it's great what they're doing to drive innovation, to get interdisciplinary teams working together. Like we talk about it, you know, the Nexus, Julio Tino. There you go, Julio, again, and yet another shout out to you in your book. But the importance of interdisciplinary teams coming together and leaning on each other to solve the biggest challenges in the world. I'm juiced, man. I'm psyched at what I heard. What about you? What did you learn? What did you take away?
Yeah, ditto. I always love a quantum computing conversation because I always leave it questioning how my intelligence and how little I know about it. But building on the previous episodes, every time we have one, I learn a little bit more. I love the power of competition. I think that there should be more competition. I think that it starts at home. And that's why I encourage my kids to compete, because it obviously drives innovation. And quantum's particular because all the other technologies we have on the show, we speak about AI a lot, robotics, blockchain. This is all happening. This is beyond theory. This is changing companies, changing lives, changing how we work and play. And quantum kind of, we're just waiting for it. It's all about potential. And I think with the XPRIZE, there's this concrete move to move it out of the lab and into the real world, however that might be. So I'm excited about that. I don't know about how you think about quantum, but on the one hand, you've got, it's going to be 20 years, 30 years before we have anything useful. On the other hand, you've got people like Kathrin and XPRIZE saying, oh, nah, we don't need to wait that long. We can do things now. It's encouraging.
The term useful is bunk. It reminds me of
Yes.
like I'm picturing you and I sitting at a conference table. We're pitching to a VC, and you know it's this brilliant idea, and the VC's tapping his fingers, going, "Well, when is this going to be built, Mark? When is it going to be useful?" Right? Everything that the quantum computing world, in my opinion, is doing is on a path to usefulness or utility. Right? Like every little step is getting us, you know, to a point where it's going to change a lot of things that we don't even know it's going to change yet. But I'm going to reel it back in just a touch, but like pointing back to the quantum processes we don't understand. Kathrin mentioned photosynthesis. We broke down photosynthesis from Michio Kaku's book. Like the power, nature does that stuff really well, right? And we try to repeat natural systems, and they end up being pretty clunky at first, but eventually, you know, we get a little bit better at them and we learn a little bit more and that sort of thing. So like the party's just getting started, in my opinion.
Well, yeah, like you said, nature is awesome at quantum mechanics. Nature is quantum mechanics, and maybe all the information we need is just out there. We just need to find a way. Whenever we have conversations about humanity's greatest challenges, I always think about the doomsday clock and the ticking, you know? And can we wait 20 years? Can we wait 50 years? Should we, as a species, be waiting 50 years? Because if you spent all your life reading headlines in the mainstream media or in any kind of press, you'd think, no, we don't have very much time. Actually, we need to get this cooking now. We need to get it out of the lab now. We need to be doing this now, because humanity's greatest challenges today might be a whole lot worse in 5, 10, 15, 20, 25 years.
Well, this is Wormhole Adventures by Jeremy and Mark. But like here's something. Here's the theory. We talked about this a little bit today. Is the idea that the human equation, the human piece of the equation, no matter what technology we're using, there are things that we do human to human. You know, information networks. We're reading, you know, Nexus right now and talking about information systems and disinformation and all of that. I would argue we could buy ourselves more time by figuring out that piece, which is easier to fix than figuring out how to use qubits to solve a problem that a VC is going to get excited about and fund.
Oh, I like that. Yeah, using information networks to buy humanity some time. You're gonna have to expand on that. What might that look like? Education?
I think it boils down to a couple things. I think it boils down to critical thinking. I think it boils down to empathy. Empathy is the biggest missing piece between one person and the other, right? If I'm not truly empathetic in your position, I'm not listening to you. All I'm doing is reloading what I think is correct and firing it at you, right? And as long as there's that disconnect, and I'm not saying the world isn't empathetic. They're empathetic people, right? But I think if we can improve our empathy as a superpower moving forward, that position could buy us time to make better decisions on behalf of society to allow some of these great things to happen.
I can't remember the guest, but I remember we had a conversation about this and how AI augments or dilutes our empathy. And I think the consensus that we drew was it decreases our empathy. I don't know if you remember that show. I've got a video somewhere of you saying that, or our guest saying that it decreases empathy. So if we need more empathy and you had a big, good, nice rant about that last week, by giving over our critical thinking, by giving over our choices to AI, we actually decrease our empathy.
We could have a whole study on that. Maybe we'll submit an application to an XPRIZE and they'll give us some money and we can make it happen. But
I bring back the doomsday clock.
Oh my gosh. Well, this is guys. I hope you're enjoying this. Thinkingonpaper.xyz. We want to hear from you. We started this show for us. We are now delivering it and producing it for you. We want this to be a valuable tool for help you to figure out these technologies and also what it means to our humanity and what the world's going to look like moving forward. Thinkingonpaper.xyz. Let us know how you feel. Share a guest, share it with a friend if you hear something cool, right? Anything else, Mark?
Like, subscribe, thinkingonpaper.xyz. Drop us a comment, drop us a complaint, drop us an idea, drop us a dream. Just write a comment and we'll answer it next week. And all I have to say is stay disruptive, be curious,
keep thinking on paper. Till next time.
Right.